Let's go ahead and go over some of our quality management and control slides. I am going to skip over the examples since I already made some other videos, trying my best to explain those. So first off, what is quality? So here's our main definitions. The first one is fitness for use. This is going to be customer centric. So this is customer centric. Conformance to requirements is producer centric. And so what that would mean is a toaster would conform to the wiring specs. That's the conformance. And then in terms of fitness for use, it's going to be how well it toasts bread, if it properly does it and satisfies the customer. Then if we go ahead and move on to product dimensions, we see that they define a product's core functionality and consistency. So performance is the primary function, features are added extras, and then reliability is the measure of consistent operation over time. If we take a look at a laptop, the fast processor is the performance. That is its main function. We want our laptop running fast. If it comes with a built-in stylus, that's a feature. It's a little extra something that they added in there. And then working 1,000 hours without a crash is going to be reliability. That means it's consistent. It keeps working for 1,000 hours. It's not crashing. And then if we move forward, we have some more dimensions such as durability. This is its lifespan. The serviceability, ease of repair, aesthetics, which is the visual appeal, and then safety, meaning it's not going to harm anyone. So durability would be something saying it has a 15-year lifespan. If we go back to that laptop, will it have a 15-year lifespan? I don't know how realistic that is, but that means it's pretty durable. If it's quick and easy to repair and it's not super expensive, that is serviceability. And then if it's going to be a very fancy, pretty laptop, stainless steel, is that proper for a laptop? Doesn't matter. That is our aesthetics. So if we move forward, now we have some dimensions of quality for service. So what this means is it's going to be judged by human interaction, delivery speed, and overall perception of something. Some important components are going to be convenience, reliability, assurance, and expectations. What that might mean is, so in a bank, if you have a lot of ATMs, that's convenient. Everyone can access it easily. They don't have to wait for a long time. But a teller accurately processing a deposit, that's reliability. Again, it's that accurately right there. Assurance would be provider knowledge, and again, expectations is going to just be making sure those are all met. As we move forward to quality and productivity, historically, quality was seen as conflicting cost center. Often it was just a late stage inspection process. Because fixing defects was costly, it was believed that you had to sacrifice productivity, which would be speed, to gain quality, which was actually a false trade-off. So that one's a little more self-explanatory, so I won't do an explanation for that one. We can just go ahead and move on to cost of poor process performance. So this would include certain things such as prevention, which is proactive investments, appraisal, which is inspection, internal failure costs are defects caught before the customer, and external failure costs. This is the most damaging kind, and those are defects that are found by the customer. So prevention cost is going to be staff training. So that's our proactive investment. We're making sure that our staff are trained properly to create whatever we're making the best they can. But testing the product before shipping is going to be an appraisal cost. That's an inspection. So let's say it's a laptop. Before even shipping it out, we are going to want to make sure it works. Handling a customer refund would be an external failure cost. That's because they didn't check that laptop, they sent it out, and it was already broken. So they had to return it and refund that customer. These are some of Deming's 14 points. I don't have much to add to this part, so I'm going to go ahead and skip through these. And then we have some of our methods for generating ideas. Brainstorming would encourage unrestrained group thinking. Quality circles are worker groups that are focused on process improvement, and then benchmarking compares performance against the best industry standard. So an example would be a team would hold a brainstorming session. They'd kind of just go together, all talk, and see what's best. Whereas benchmarking is, again, we'll use the laptop. So we want to compare our laptop performance to what the industry currently finds the best. Next, we move on to our statistical process control. This is a system of techniques for monitoring and improving production and service processes. The main goal is to measure and evaluate a process's capability, indicate when it is in control, and increase the efficiency. So a factory would use this to track the weight of potato chip bags to ensure consistency and also minimize the waste we're having. And then we move on to a process control chart. This is going to be the key tool of statistical process control. We are plotting sample statistics over time to differentiate between random and non-random variation. We're doing this to assure the process output is random and stable. We know this because we're placing upper and lower control limits, defining the range of acceptable and then expected variation. A chef plots oven temperature readings to ensure the process remains within the acceptable upper and lower control limit during baking. Once again, that upper and lower control limit is essentially a fence. We want to stay inside and we want to make sure it's random. If it's non-random, it's possible that maybe something's broken. And that kind of brings us on to our next slide, which is causes of variation. There are two categories, common causes and assignable causes. So common causes are the random, unavoidable fluctuations, and assignable causes are identifiable. So these would be like a broken machine or someone that was untrained. So slight daily variations, like in coffee temperature, like we'll go back to McDonald's, they're giving you your coffee, it's going to be slightly different. Those are common causes. That's just what happens. But a sudden drop in the temperature because of the faulty heating, now that machine is broken, that's an assignable cause. That's why the coffee is not as hot as it should be. Then we move on to our appropriate uses of SPC. So it's most effective when it's applied to processes that are measurable, repetitive, and have a quantitative output. It should also be prone to occasional drift or dramatic shifts to benefit from the continuous monitoring. Then we can move on to, if it'll let me, the steps in creating control charts. Okay, so the main steps involve sampling the process, calculating and drawing the control limits, and then plotting the sample results. The key is to investigate and correct any points that may fall out of control. This is outside of those upper and lower limits before establishing new stable control limits. So control charts for attributes. I'm not going to solve this problem, I'm just explaining. So when we are measuring continuous data, these are our variables. There are two primary charts that we're going to be looking at, which is our X-bar chart and our R chart. The X-bar chart monitors the central tendencies, which is average of the process, while the R chart monitors the process dispersion. This is the range or the variation. So we would use the X-bar chart to track the average bolt diameter and the R chart to track the consistency or the range of those diameters. Then we can actually, I'm not skipping, but I am skipping. This is still control chart attributes. So now I'm going to go forward to process capability. Again, these are the X and the bar charts. And then these are putting it all together in examples. And then we have process capability. So the capability analysis is performed only after a process is shown to be statistically in control. This means it shows only random variations. It determines if the process's inherent variation is small enough to fit within the design specifications. If it is, that means the process is capable. So for example here, after we confirm the stability, a study will show that 99.73% of output falls within the customer's acceptable tolerance range, meaning it would be capable. And if our range range of possible solutions. So if a process is not capable, the manager then will have several options about how to go about things. They can redesign it, or they can adopt a different process altogether. A short-term fix would include relying 100% on inspections to filter out the bad input, or they can re-examine it and maybe relax the specifications. So, for example, to fix a non-capable process, the company might buy a new or more precise machine. I believe that's everything I have for this one. Oh, sorry, that was the range of possible solutions. That's what it would have been as I was just going over it. I think that's everything. I think the rest is just examples. Yes, it is. So hopefully that helps.